Look up at the night sky tonight, far from the glare of city lights, and you will see what has captivated humanity for 5,000 years. Above you, countless points of light pierce the darkness, each star holding its place in patterns that have remained unchanged since our species first walked upright. The Great Bear still prowls the northern sky. Orion still stands guard over winter nights. These stellar monuments have watched over every human civilization, unchanging and eternal. But among these fixed sentinels, ancient eyes discovered something extraordinary, something that challenged everything our ancestors believed about the heavens above. 5,000 years ago, in the river valleys of Mesopotamia, patient astronomers noticed that 5 particular points of light refused to obey the cosmic order. While every other star maintained its designated place in the grand celestial tapestry, these 5 rebels wandered. Night after night, month after month, they traced mysterious paths across the sky, sometimes moving steadily forward, sometimes stopping entirely, sometimes even reversing direction and traveling backward against the flow of stars. The Babylonians, masters of mathematical precision, who could predict eclipses centuries in advance, gave these cosmic wanderers a name that reveals their bewilderment. They called them Mul-Lubat, the wild sheep. Like sheep that stray from the flock, these luminous points had abandoned their assigned positions and roamed freely through the stellar pastures. Imagine the profound unease this discovery must have caused. For people who depended on the stars for navigation, for marking the seasons, for understanding their place in creation, these wandering lights represented chaos in a perfectly ordered universe. Yet something about their behavior suggested they followed rules of their own, patterns within patterns, cycles within cycles. The brightest wanderer blazed with the brilliance of a cosmic beacon. We know it, today, as Venus, but to ancient observers, it seemed to be 2 separate stars. They watched it appear as a brilliant herald of dawn, rising before the sun for months at a time, only to vanish and reappear weeks later as an evening star, hanging in the western sky after sunset. This transformation from morning star to evening star felt like witnessing cosmic magic. Another wanderer glowed with a distinctly reddish light that seemed to pulse and flicker. The Babylonians called it Nergal, after their god of war, sensing something ominous in its bloody hue. We know this wanderer as Mars, and its red light comes from iron oxide, rust, covering a world that once flowed with rivers and may have harbored life. The fastest wanderer raced across the sky, never straying far from the sun, appearing briefly at dawn or dusk before vanishing into solar glare. Mercury, as we call it today, completes its orbit in just 88 Earth days, making it the swiftest of all worlds in our cosmic neighborhood. 2 more wanderers moved with stately grace across the stellar background. One shone with steady golden light, taking nearly 12 years to complete its journey among the constellations. Another moved even more slowly, requiring almost 30 years for a single circuit. These distant wanderers, Uranus, Jupiter and Saturn, seemed to govern vast celestial territories, their movement so gradual that a human lifetime barely witnessed a fraction of their cosmic dance. For over 2,000 years, the greatest minds of antiquity struggled to understand these wandering stars. The Greek word planetis meant wanderer, and from this we derive our modern word planet. But calling them wanderers only described their behavior, or not explain why they wandered. The Greek astronomer Hipparchus, working on the island of Rhodes around 150 BCE, made observations so precise that we still use his star catalogue today. He tracked the wanderers with mathematical rigor, discovering that their seemingly chaotic movements actually followed complex but predictable patterns. Each wanderer traced loops against the background stars, moving forward for months, slowing to a stop, moving backward for a time, then resuming forward motion. These retrograde loops puzzled astronomers for centuries. The mystery deepened when observers realized that the wanderers showed phases, like the Moon. Venus, viewed through the earliest telescopes, revealed itself as a crescent, then half illuminated, then full, then crescent again. This could only happen if Venus orbited the Sun, not Earth. The implications were staggering. If Venus circled the Sun, then perhaps all the wandering stars did the same. Consider for a moment what this revelation meant to our ancestors. For millennia, humans had believed Earth stood at the center of creation, with all celestial objects orbiting around us. We were the focal point of divine attention, the reason for cosmic existence. But the wandering stars suggested a different reality, and Earth itself might be a wanderer, one world among many, orbiting a distant star we happen to call the Sunday. The breakthrough came from an unlikely source. Aristarchus of Samos, working 3 centuries before Christ, attempted something no one had tried before, measuring the actual distances to celestial objects. Using elegant geometry and careful observations of lunar eclipses, he calculated that the Sun was 18 times farther from Earth than the Moon. His measurement was wrong by a factor of 20, but it was the first scientific attempt to gauge cosmic distances. More importantly, Aristarchus realized that if the Sun was much larger than Earth, it made sense for Earth to orbit the Sun, not the reverse. For 2,000 years this idea lay dormant. The notion that Earth moved seemed to contradict everyday experience. We feel no motion, experience no cosmic wind rushing past us as we hurtle through space. The ground beneath our feet feels solid and stationary. Only a few visionary thinkers dared suggest that appearances might deceive us. Then, on a cold January night in 1609, everything changed. Galileo Galilei, a mathematics professor from Padua, pointed a crude telescope toward Jupiter and witnessed something that would forever alter humanity's understanding of its place in the cosmos. Through his primitive 20-power telescope, APT, little better than a child's toy by modern standards, Galileo saw 4 tiny points of light arranged in a straight line beside Jupiter. Night after night, he watched these points change position, sometimes appearing on one side of Jupiter, sometimes on the other, sometimes disappearing entirely behind the giant planet. Galileo was witnessing something unprecedented in human experience. ADEs, worlds orbiting another world. These 4 moons of Jupiter, Io, Europa, Ganymede, and Callisto, provided the first direct evidence that Earth was not the center of all celestial motion. Here was Jupiter, itself a wandering star, accompanied by its own retinue of satellites dancing attendance around it. The implications struck like lightning. If Jupiter could have moons orbiting it while Jupiter itself orbited the Sun, then the cosmos was far more complex and beautiful than anyone had imagined. We were not witnessing the movements of distant lights painted on a celestial sphere. We were observing entire worlds, each with its own gravitational influence, each following the precise mathematical laws that governed all motion in the universe. These 4 points of light, barely visible in Galileo's telescope, became humanity's first glimpse of alien landscapes. Io, we now know, erupts with sulfur volcanoes that spew material 300 kilometers into space. Europa hides a global ocean beneath its icy shell, containing twice as much water as all Earth's oceans combined. Ganymede generates its own magnetic field and may harbor a subsurface sea. Callisto preserves the record of cosmic bombardment dating back 4 billion years. But in 1609, they were simply 4 moving dots that shattered the ancient worldview. Each night, Galileo watched them dance their orbital ballet around Jupiter, providing irrefutable proof that the wandering stars were not mysterious lights but entire worlds, each following its own cosmic choreography. The wandering stars had revealed their greatest secret. They were not divine messengers or harbingers of earthly events. They were places, actual worlds with surfaces and skies, gravity and weather, perhaps even life. The 5 wanderers visible to ancient eyes were our nearest neighbors in a cosmos filled with countless worlds orbiting countless stars. Venus, the brilliant herald of dawn, was a world wrapped in dense clouds, hiding a surface hot enough to melt copper. Mars, the bloody wanderer, was a rusty desert world where dust storms could engulf entire hemispheres for months at a time. Mercury, the swift messenger, was a world of extremes, where one side faced eternal day while the other knew only night. Jupiter and Saturn were revealed as gas giants, worlds without solid surfaces, their thick atmospheres swirling with storms larger than Earth itself. Each wandering star had become a destination, ETA, a place future generations might one day visit, explore, and perhaps even call home. The ancient mystery of the wandering stars had transformed into the modern science of planetary exploration. As you lie beneath tonight's sky, remember that the same wandering stars that puzzled Babylonian astronomers still trace their paths overhead. Venus still blazes as the morning or evening star. Mars still glows with its ruddy light. Jupiter still majestles across the sky with its 4 bright moons dancing attendants. Saturn still wanders among the distant stars, its magnificent rings invisible to the naked eye, but there nonetheless. But now we know their secret. They are not wandering lights, but wandering worlds, each with its own story, its own character, its own place in the grand cosmic family of planets. And perhaps most remarkably of all, we have learned that our Earth is one of them, a blue wandering star carrying all of life through the vast darkness of space. The ancient mystery of the wandering stars opened humanity's eyes to a universe far stranger and more wonderful than our ancestors ever dared imagine. It was the beginning of a journey that would eventually lead us to discover thousands of other worlds orbiting distant stars, worlds that might harbor life, worlds that might become humanity's next great destinations. But that journey into the cosmic unknown began 5,000 years ago, when patient observers first noticed 5 bright points of light that refused to stay in their assigned places among the stars. Those wandering stars called to something deep in the human spirit, our insatiable curiosity about what lies beyond the horizon, our determination to understand our place in the grand scheme of creation. The wanderers had issued an invitation to explore, and explore we have. 4.5 billion years ago, in a quiet corner of what would become the Milky Way's Orion Arm, something extraordinary was about to begin. Where our solar system now gracefully orbits the galactic center, there existed only a vast cold cloud of gas and dust, a stellar nursery stretching 5 light-years across, dark and seemingly lifeless. This was no ordinary emptiness. Within this cosmic cloud, called a molecular nebula, hydrogen and helium mixed with the ashes of ancient stars, carbon, oxygen, silicon, iron, and dozens of other elements forged in stellar cores and scattered into space by supernovae. These were the ingredients of worlds, waiting patiently in the cosmic cold for something to bring them together. The cloud drifted through space for millions of years, slowly rotating, gradually cooling, growing denser as its own gravity began to pull inward. Temperatures dropped to just 10 degrees above absolute zero, colder than the deepest Antarctic winter, colder than liquid nitrogen, so cold that even hydrogen molecules moved sluggishly through the cosmic fog. Then, without warning, everything changed. Somewhere nearby, perhaps 20 light-years away, a massive star reached the end of its life. In a cataclysmic explosion that outshone entire galaxies, this stellar giant scattered its remains across hundreds of light-years of space. The shockwave from this supernova raced outward at thousands of kilometers per second, carrying with it the heavy elements forged in the star's final moments. When this cosmic tsunami struck our peaceful molecular cloud, it compressed the gas and dust like a giant hand squeezing a sponge. Imagine the violence of this compression. 2 slices, material that had drifted quietly for eons, suddenly crushed together with tremendous force. The shockwave triggered something that had been waiting to happen for millions of years. Gravity, that most patient of cosmic forces, finally gained the upper hand. What followed was one of the most spectacular transformations in the universe: the collapse of a stellar nursery into a planetary system. The compression happened with surprising speed on cosmic timescales. Over roughly 100,000 years, a mere instant in the life of the galaxy, the 5-light-year cloud shrank to a disk just 100 astronomical units across. As it collapsed, the cloud began spinning faster and faster, like a figure skater pulling in her arms during a spin. Conservation of angular momentum, AGT, one of the fundamental laws of physics, EGT, demanded that as the cloud shrank, it must spin more rapidly. What started as a barely perceptible rotation became a cosmic whirlpool, with material spiraling inward toward the center, while simultaneously flattening into a disk. This disk glowed with the heat of compression, transforming gravitational energy into thermal energy that warmed the swirling gases. At the center of this maelstrom, something remarkable was taking shape. As more and more material fell inward, the central region grew denser and hotter. Nuclear fusion flickered to life when the core temperature reached 10 million degrees Celsius. Our sun had ignited, but this newborn star was nothing like the steady, reliable sun we know today. The early sun was a violent, unpredictable infant, prone to tremendous outbursts that sent streams of charged particles racing through the surrounding disk. Solar winds, 1,000 times stronger than today's, buffeted the orbiting material, stripping away gases and reshaping the cosmic architecture. Meanwhile, in the disk surrounding this temperamental young star, the real magic of planetary formation was beginning. The disk was not uniform. Like cream slowly separating in coffee, different materials settled at different distances from the center based on their ability to withstand heat. Close to the sun, where temperatures soared above 3,000 degrees Celsius, only the most refractory materials could survive, metals and rocky minerals that could endure the stellar furnace. Further out, beyond what astronomers call the frost line, water could freeze into ice, and even more distant regions allowed methane and ammonia to condense. This temperature gradient would determine the very nature of the worlds that formed. The inner regions would birth small, rocky planets built from metals and silicates. The outer regions would create gas giants, massive worlds that could capture and hold vast atmospheric envelopes of hydrogen and helium. But first, something had to transform microscopic dust grains into planet-sized worlds. The process began with particles smaller than a human hair, cosmic dust grains that had condensed from stellar winds and supernova explosions. These tiny motes drifted through the protoplanetary disk like snowflakes in a cosmic blizzard. When they collided, something remarkable happened. Static electricity, the same force that makes socks cling together in a dryer, caused them to stick. Grain by grain, these cosmic dust bunnies grew. A speck the size of a bacterium acquired another grain and became the size of a virus. The virus-sized particle captured more grains and became microscopic. The microscopic particle grew into something visible to the naked eye. This patient accumulation continued for thousands of years. As these growing aggregates reached pebble size, gravity began to play a role. Larger pebbles attracted smaller ones, growing faster and faster in a process called runaway accretion. The rich got richer, the massive got more massive, and soon the disk was populated by objects the size of boulders, then buildings, then mountains. These mountain-sized building blocks, called planetesimals, transformed the protoplanetary disk into a cosmic shooting gallery. Moving at velocities of several kilometers per second, collisions between planetesimals released tremendous energy. When two mountain-sized objects collided at 10 kilometers per second, the impact generated enough heat to melt rock instantly. The collision site became a lake of lava, hundreds of kilometers across, glowing white-hot against the cosmic darkness. Consider the violence of this epoch. Today's solar system seems peaceful and orderly, with planets following predictable elliptical orbits that have remained stable for billions of years. But 4.5 billion years ago, chaos reigned. Thousands of planetesimals, some as large as small countries, crisscrossed orbital space in a complex gravitational dance. Every few thousand years, major collisions sent debris flying throughout the inner solar system. The first planets to emerge from this cosmic demolition derby were the gas giants, Jupiter and Saturn. Jupiter, in particular, grew with extraordinary speed. Located just beyond the frost line where water ice could condense, Jupiter had access to both rocky materials and abundant ice. This combination allowed it to grow rapidly until it reached a critical mass, Earth's CZA, roughly 10 times Earth's mass, where it could begin capturing gas directly from the surrounding nebula. Once Jupiter began accreting gas, its growth became explosive. Within a few million years, it had captured an atmosphere more massive than the rest of the planets combined. Jupiter became a gravitational giant, its influence extending throughout the solar system, and that influence was profound. Jupiter's gravity stirred the asteroid belt into perpetual chaos, preventing the formation of another planet between Mars and Jupiter. It flung icy comets from the outer solar system into the inner regions, delivering water and organic compounds to the forming terrestrial planets. Most dramatically, Jupiter's gravitational perturbations may have caused what astronomers call the Grand Tack, a period when Jupiter migrated inward toward the Sun, then reversed course and moved outward again, reshaping the entire architecture of the inner solar system. Saturn formed more slowly, but grew to rival Jupiter in size. Together, these two gas giants dominated the outer solar system, their combined gravity orchestrating the formation of countless smaller worlds, the moons that orbit them today. In the inner solar system, the terrestrial planets faced a different challenge. Here, closer to the Sun, temperatures were too high for gas accretion. These worlds had to be built the hard way, through countless collisions between rocky planetesimals. Mercury, closest to the solar furnace, formed from materials that could withstand extreme heat, iron, nickel, and refractory silicates. Venus and Earth, farther from the Sun, incorporated more diverse materials, including water delivered by icy comets from the outer system. Mars began as a promising world. Early in its formation, it accumulated enough mass to generate substantial heat from radioactive decay and gravitational compression. This heat melted its interior and may have sustained a magnetic field that protected its early atmosphere. Rivers carved channels across its surface, and ancient lake beds suggest that Mars once enjoyed a warm, wet climate that could have supported life. But Mars faced a fundamental limitation, its EZA. Its small size, with only half Earth's diameter and 11% Earth's mass, Mars could not retain a thick atmosphere indefinitely. Over hundreds of millions of years, its atmosphere slowly leaked away into space, leaving behind the cold, thin air we observe today. The most dramatic event in the early solar system was yet to come. Roughly 50 million years after the Sun ignited, when the inner planets had largely finished forming, a Mars-sized planetesimal called Theia followed an unstable orbit that crossed Earth's path. The collision, when it came, was apocalyptic beyond imagination. Theia struck Earth with a velocity of roughly 15 kilometers per second, 50 times faster than a rifle bullet. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously. Both worlds were completely destroyed, vaporized into a cloud of molten rock and metal that briefly formed a ring around the newly formed Earth-Moon system. This was not merely destruction but cosmic creation of the most spectacular kind. As the vaporized rock cooled and condensed, it formed a ring of debris around Earth. Over thousands of years, this ring gradually coalesced into a single large satellite, our Moon. The Moon's formation solved several puzzles about Earth's unique characteristics. The collision tilted Earth's rotation axis, giving us seasons. It increased Earth's day length and established the tidal forces that may have helped early life emerge from the oceans. The Moon also stabilized Earth's climate by preventing large changes in the planet's axial tilt. But perhaps most importantly, the Moon bears witness to the violent birth of planets. When you look up at the Moon tonight, you are seeing the result of the most catastrophic collision in our solar system's history. Is a no. Two worlds destroyed to create the Earth-Moon system that made life possible. By 4 billion years ago, the era of planetary formation was largely complete. The remaining planetesimals had either been incorporated into planets, ejected from the solar system by gravitational encounters, or relegated to stable orbits in the asteroid belt and Kuiper belt. The solar system had found its rhythm, but this apparent peace was deceptive. The late heavy bombardment was about to begin, a period of renewed chaos when Jupiter and Saturn's gravitational interactions destabilized populations of asteroids and comets, sending them careening through the inner solar system. For 500 million years, Earth, Mars, Venus, and Mercury endured constant bombardment. Objects larger than cities struck Earth every few million years, vaporizing oceans and sterilizing the surface. The largest impacts created basins hundreds of kilometers across and threw debris completely around the planet. Yet even this cosmic violence served a purpose. The bombardment delivered water, organic compounds, and other materials essential for life. Each impact was simultaneously destruction and delivery, clearing the slate for new possibilities while providing the raw materials for complexity. As the bombardment finally subsided 3.5 billion years ago, the solar system entered the long period of stability we know today. The violent birth was over. The stellar furnace had forged 8 major planets, dozens of moons, and countless smaller worlds from the cold molecular cloud that had drifted quietly through space for millions of years. This transformation, AI, from dark nebula to planetary system, represents one of the most remarkable processes in the universe. Within just a few 100 million years, gravity and the fundamental forces of physics had organized cosmic dust into a hierarchical system of extraordinary complexity and beauty. Every grain of sand on Earth's beaches, every drop of water in its oceans, every atom in your body was forged in this cosmic furnace. You are made of star stuff, quite literally. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in stellar cores and delivered to Earth during the solar system's violent birth. The next time you witness a sunrise, remember that you are watching light from a star that ignited in the gravitational collapse of a molecular cloud 4.5 billion years ago. The ground beneath your feet was assembled grain by grain through countless collisions in a protoplanetary disk. The Moon overhead formed when 2 worlds died so that Earth might live. Our planetary system is both the product of cosmic violence and cosmic creativity, destruction and construction, dancing together in the stellar furnace where worlds are born. In the aftermath of the cosmic violence that forged our solar system, 4 rocky worlds emerged from the stellar furnace, each carrying the potential for vastly different destinies. Like siblings born into the same family yet shaped by their unique circumstances, Mercury, Venus, Earth, and Mars embarked on evolutionary journeys that would determine not just their physical characteristics, but their very capacity to nurture and sustain life. The story of these 4 worlds is a tale of cosmic chance and inevitable physics, of planets that began with similar building blocks, yet found themselves traveling paths that led to paradise, perdition, and everything in between. It is a story that reveals how the smallest differences in cosmic circumstances can lead to the most profound differences in planetary fate. Let us begin with Mars, the world that perhaps came closest to matching Earth's early promise, but ultimately chose a different path through cosmic time. 4 billion years ago, Mars was a never world transformed. Where today we see only rust-colored deserts and ancient impact craters, early Mars knew the sound of flowing water. Rivers carved serpentine channels through volcanic highlands. Vast lakes collected runoff from Martian watersheds. Some scientists believe an ocean may have covered the planet's northern lowlands, making Mars a blue world orbiting beyond Earth's sphere of influence. This ancient Mars enjoyed a thick atmosphere, perhaps denser than Earth's atmosphere today. Carbon dioxide blanketed the planet, creating a greenhouse effect that kept surface temperatures well above freezing, despite Mars receiving only 43% as much sunlight as Earth. Water vapor rose from lakes and rivers, forming clouds that brought rain back to the Martian surface. The planet possessed a global hydrological cycle that might have operated for hundreds of millions of years. Consider what this means. For longer than complex life has existed on Earth, Mars may have offered conditions suitable for the emergence and evolution of life. If microbes arose in Martian rivers or lakes, they would have had ample time to diversify, to adapt, perhaps even to evolve into more complex forms. But Mars carried within itself the seeds of its own atmospheric destruction. Being only 11% as massive as Earth, Mars could not hold on to its thick atmosphere indefinitely. The planet's small size meant weaker gravity, less able to retain gas molecules that gained enough energy to escape into space. More critically, Mars's small mass meant its interior cooled relatively quickly. As the planet's core solidified, its magnetic field gradually weakened and eventually disappeared entirely. Without this magnetic shield, Mars became vulnerable to the solar wind, the streams of charged particles flowing constantly from the Sun at speeds of several hundred kilometers per second. Over hundreds of millions of years, the solar wind systematically stripped away Mars's atmosphere. High-energy particles knocked atmospheric molecules loose and carried them into space. The process was slow but relentless, like a cosmic wind gradually eroding a mountain. Today, atmospheric pressure on Mars is less than 1% of Earth's pressure. The air is so thin that liquid water cannot exist on the surface, except perhaps briefly during the warmest parts of Martian summer. Temperatures plunged to -125 degrees Celsius at the poles, cold enough to freeze carbon dioxide into dry ice. Yet Mars has not forgotten its aquatic past. Spacecraft orbiting the planet have revealed ancient riverbeds, dried lake beds, and mineral deposits that could only have formed in the presence of liquid water. Perhaps most tantalizingly, some of these deposits contain clays and other minerals that on Earth are associated with biological activity. The story of Mars is a story of atmospheric loss and climatic collapse, but it is also a story of persistence. Evidence suggests that even after losing most of its atmosphere, Mars continued to experience periods when liquid water flowed across its surface. Deep underground, liquid water may still exist today, warmed by radioactive decay in the planet's interior. If life ever arose on Mars, it may have retreated underground as surface conditions deteriorated. In the subsurface realm, shielded from radiation and possibly warmed by geothermal energy, Martian life might persist even today. Venus tells a very different tale, a story of runaway climate change that transformed Earth's twin into a hellish furnace. Early in solar system history, Venus may have been the most Earth-like world of all. Similar in size and mass to our planet, orbiting at a distance where liquid water could theoretically exist, Venus began with abundant water delivered by comets and asteroids during the late heavy bombardment. Computer models suggest that if Venus rotated faster in its youth, it might have maintained liquid oceans for billions of years. A faster rotation would have generated stronger atmospheric circulation, distributing heat more evenly between day and night sides, and preventing the extreme temperatures that plague the planet today. But Venus harbored a fatal flaw, Amal, its proximity to the Sunday receiving twice as much solar radiation as Earth. Venus walked a tightrope between habitability and catastrophic greenhouse warming. Any increase in atmospheric carbon dioxide could tip the balance toward disaster. The trigger may have been volcanic outgassing. Venus experiences volcanism on a scale that dwarfs Earth's geological activity. Massive volcanic provinces cover substantial portions of the planet's surface. When these volcanoes erupted, they released enormous quantities of carbon dioxide into the atmosphere. On Earth, carbon dioxide released by volcanoes eventually gets recycled. Rain combines with atmospheric carbon dioxide to form weak carbonic acid. This acid dissolves rocks and carries carbon into the oceans, where it forms carbonate minerals on the seafloor. Plate tectonics then subducts these carbonates back into the mantle, completing the carbon cycle. Venus lacks this carbon recycling system. Without liquid water, there can be no carbonic acid weathering. Without plate tectonics, there is no mechanism to remove carbon dioxide from the atmosphere. Carbon dioxide from volcanic eruptions simply accumulates, creating an ever-thickening blanket of greenhouse gases. As atmospheric carbon dioxide increased, surface temperatures rose. Higher temperatures increased the rate of water evaporation. Water vapor is itself a powerful greenhouse gas, trapping even more heat and driving temperatures higher still. This positive feedback loop, EPUS, called a runaway greenhouse effect, transformed Venus from a potentially habitable world into an inferno. Today, Venus's atmosphere is 96% carbon dioxide, with surface pressures 92 times Earth's atmospheric pressure. Standing on Venus's surface would feel like being crushed under nearly a kilometer of water. Temperatures reach 460 degrees Celsius, hot enough to melt lead, hot enough to destroy any spacecraft that attempts to land on the surface. Sulfuric acid clouds perpetually shroud the planet, raining acid that evaporates before reaching the ground. Lightning flickers constantly through these corrosive clouds. Venus has become a cautionary tale of climate change taken to its most extreme conclusion. Yet even this hellish world maintains an eerie beauty. Beneath its acid clouds, Venus reveals a landscape of ancient impact craters, massive volcanic shields, and mysterious circular features called coronae that may mark sites where mantle plumes have pushed upward against the crust. Venus reminds us that planetary climates can be delicately balanced systems. Small changes can trigger large consequences. A world that began much like Earth found itself on a path toward atmospheric catastrophe from which there appears to be no return. Mercury, the innermost world, tells yet another story, a tale of extremes that reveals how planets adapt to the harshest cosmic environments. Orbiting just 58 million kilometers from the Sun, Mercury receives more than 6 times as much solar radiation as Earth. During its 88-day year, surface temperatures on the day side soar to 427 degrees Celsius. This is hot enough to melt zinc, hot enough to vaporize many metals. But Mercury's slow rotation, it spins just once every 59 Earth days, means that each hemisphere experiences prolonged periods of day and night. On the night side, with no atmosphere to retain heat, temperatures plummet to minus 173 degrees Celsius. This temperature range of 600 degrees Celsius is the largest of any planet in the solar system. Mercury's extreme temperature variations would seem to make it one of the most hostile worlds imaginable. Yet recent discoveries have revealed surprising complexity. Radar observations from Earth detected bright patches at Mercury's north and south poles that appear to be deposits of water ice. On a world where daytime temperatures can melt lead, water ice survives in permanently shadowed craters where the sun never shines. These ice deposits may preserve a record of comet impacts spanning billions of years. Each comet that struck Mercury delivered not just water but organic compounds, the carbon-based molecules that serve as building blocks for life. Mercury's polar ice may contain a frozen library of the organic chemistry that once filled the early solar system. Mercury also poses puzzles about planetary formation. Its iron core comprises 61% of the planet's radius, ATS, a much larger proportion than any other terrestrial planet. This oversized core suggests that Mercury may have formed farther from the Sun and migrated inward, or that a massive impact stripped away much of its rocky mantle early in solar system history. Despite its harsh environment, Mercury demonstrates that even the most extreme worlds can harbor unexpected complexity. In permanently shadowed polar craters, water, ice, and organic compounds wait patiently, preserved for billions of years in the cosmic deep freeze. And then there is Earth, the world that found the perfect balance. Earth's story is one of countless fortunate circumstances that combine to create and maintain conditions suitable for life. Our planet's distance from the Sun places it squarely in the habitable zone, where liquid water can exist on the surface. But distance alone does not guarantee habitability. Earth's magnetic field, generated by convection of molten iron in its outer core, deflects the solar wind that stripped away Mars's atmosphere. This magnetic shield extends far into space, protecting not just our atmosphere but also the life it supports from deadly cosmic radiation. Plate tectonics, TSN, the slow movement of crustal plates, driven by convection in the mantle, plays a crucial role in maintaining Earth's climate. The carbon cycle I described earlier operates continuously, removing excess carbon dioxide from the atmosphere through weathering and subduction, while releasing stored carbon through volcanic outgassing. This planetary thermostat has kept Earth's temperatures within the range where liquid water can exist for over 4 billion years. Earth's large moon, formed in the catastrophic collision that destroyed Theia, stabilizes our planet's axial tilt and gives us regular seasons. Without the moon's gravitational influence, Earth's rotation axis would wobble chaotically, causing dramatic climate variations that might prevent complex life from evolving. Even Earth's position in the solar system proved fortunate. Jupiter's massive gravity deflects many comets and asteroids that might otherwise impact Earth, reducing the frequency of mass extinctions. Yet Jupiter also sends some objects toward the inner solar system, including the water-rich comets that helped fill Earth's oceans. Consider the delicate balance required to maintain Earth's biosphere. If our planet were 5% closer to the Sun, it might have suffered a runaway greenhouse effect like Venus. If it were 5% farther away, it might have frozen into a permanent ice age. If it lacked plate tectonics, carbon dioxide might accumulate until surface temperatures became uninhabitable. If it lacked a magnetic field, the solar wind might gradually strip away its atmosphere and water. Earth found the narrow path between these extremes and has walked it successfully for billions of years. But this is not a passive stability. Earth's climate system actively responds to changes, with life itself playing a crucial role in maintaining habitability. Photosynthetic organisms have transformed Earth's atmosphere from carbon dioxide-rich to oxygen-rich, fundamentally altering the planet's chemistry. The oxygen we breathe is a waste product of ancient bacteria that learned to harness sunlight. Without life, Earth's atmosphere would probably resemble that of Mars or Venus. Life has also influenced Earth's albedo, power, the amount of sunlight the planet reflects back to space. Forests absorb solar radiation, while ice sheets reflect it. Ocean phytoplankton produce compounds that seed cloud formation, affecting global weather patterns. Even the calcium carbonate shells of marine organisms help regulate atmospheric carbon dioxide levels. Earth's story is still being written. Our planet continues to evolve, its climate and atmosphere shaped by the ongoing interaction between geological processes and biological activity. The emergence of human civilization has introduced new variables into Earth's climate system, but the fundamental processes that have maintained habitability for billions of years continue to operate. These 4 worlds, Mercury, Venus, Earth and Mars, Rule M, began their journeys from similar raw materials in the same stellar nursery. Yet their different masses, orbital distances, and cosmic circumstances led them down divergent evolutionary paths. Mercury became a world of extremes, Venus a cautionary tale of runaway climate change, Mars a planet of lost possibilities, and Earth a blue oasis where life has flourished. Their stories remind us that planetary evolution is not predetermined. Small differences in initial conditions can lead to vastly different outcomes. The cosmos is filled with worlds following their own unique evolutionary trajectories, shaped by the interplay of physics, chemistry, and cosmic circumstance. As we search for life beyond our solar system, the diverse fates of our neighboring worlds provide both hope and soberness. They show us that habitable conditions can emerge and persist for billions of years, but also that they can be lost through processes we are only beginning to understand. The story of worlds finding the destiny continues to unfold, not just in our solar system but throughout the galaxy, where thousands of exoplanets are writing their own chapters in the grand narrative of planetary evolution. For over 2,000 years after Galileo first glimpsed the moons of Jupiter, humanity gazed at the night sky with a tantalizing question burning in our collective imagination. If our sun hosts a family of worlds, do other stars harbor planets of their own? The quest to answer this question would become the greatest treasure hunt in the history of science. Siomare, a search for distant worlds that would ultimately revolutionize our understanding of our place in the cosmos. The challenge seemed insurmountable. Consider the enormous difficulties facing astronomers who dared to search for planets around other stars. Even the nearest star beyond our sun lies over 4 light-years away. It was a distance so vast that if the sun were the size of a grain of sand in New York City, the nearest star would be another grain of sand in Los Angeles. At such distances, a planet appears not as a visible disk, but as an infinitesimally small point of light, if it can be seen at all. A planet orbiting the nearest star would appear roughly 1 billion times fainter than the star itself. This is equivalent to trying to spot a firefly sitting next to a powerful searchlight from a distance of 1,000 miles. For most of human history, the technology simply did not exist to meet this challenge. The most powerful telescopes of the 19th and early 20th centuries could barely resolve the disks of planets in our own solar system, let alone detect the faint glimmer of worlds orbiting distant stars. Yet astronomers persisted in their search, driven by an almost mystical conviction that planets must be common throughout the universe. If the laws of physics operate the same way everywhere, they reasoned, then the processes that formed our solar system should occur around other stars as well. The first hints came not from direct observation, but from careful measurement of stellar motion. In the 1940s, Peter van der Kamp, a Dutch-American astronomer working at Swarthmore College, began a decades-long campaign to detect the gravitational wobble that a large planet might induce in its host star. Van der Kamp focused on Barnard's star, a red dwarf located just 6 light-years from Earth. Red dwarfs are smaller and dimmer than our Sun, which means any planets orbiting them would have a more pronounced gravitational effect. If a Jupiter-sized planet orbited Barnard's star, it would cause the star to wobble back and forth by a tiny amount, less than the width of a human hair as seen from Earth. For over 30 years, Van der Kamp photographed Barnard's star thousands of times, measuring its position against background stars with painstaking precision. In 1963, he announced the discovery of a planet 1.5 times Jupiter's mass orbiting Barnard's star every 24 years. The astronomical community was electrified. Here, finally, was the first world detected beyond our solar system. But excitement turned to disappointment when other astronomers failed to confirm Van der Kamp's measurements. Systematic errors in his photographic plates had created the illusion of planetary motion where none existed. The false dawn of Barnard's star taught astronomers important lessons about the precision required for exoplanet detection. Any claimed discovery would need to be confirmed by multiple independent observations using different techniques. The bar for evidence would have to be set extraordinarily high. The breakthrough finally came in 1995, and it came from an unexpected direction. Michel Mayor and Didier Queloz, Swiss astronomers working at the Haute-Provence Observatory in southern France, were not specifically searching for planets. Instead, they were conducting a survey of stellar velocities, measuring how fast stars move toward or away from Earth using the Doppler effect. The Doppler effect is familiar from everyday experience, the changing pitch of a siren as an ambulance approaches and then recedes. Light from stars exhibits the same phenomenon. When a star moves toward Earth, its light waves are compressed slightly, shifting toward the blue end of the spectrum. When a star moves away, its light waves are stretched, shifting toward red. Mayer and Kellos were using a revolutionary new instrument called LOD, a spectrograph capable of measuring stellar velocities with unprecedented precision. LOD could detect velocity changes as small as 10 meters per second, roughly the speed of a bicycle rider. On the night of July 6, 1995, they were observing 51 Eridani, a sun-like star 50 light-years from Earth. The data showed something extraordinary. The star was oscillating back and forth with a period of just 4.2 days, alternately approaching and receding from Earth at speeds of several dozen meters per second. This regular oscillation could mean only one thing. A massive planet was orbiting 51 Eridani, causing the star to wobble as the planet's gravity tugged it back and forth. But the properties of this planet defied every theory about planetary formation. The world orbiting 51 Eridani was a giant planet, at least half as massive as Jupiter, but it completed its orbit in just 4 days. This meant it was orbiting incredibly close to its star, much closer than Mercury orbits. Our Sunday surface temperatures on this alien world would exceed 1,000 degrees Celsius, hot enough to melt copper. Astronomers had discovered the first hot Jupiter, a class of planets that theory said should not exist. According to everything scientists understood about planetary formation, massive planets like Jupiter should form far from their stars, beyond the frost line, where water can condense into ice. The solid cores of gas giants need access to abundant ice to grow large enough to capture thick hydrogen atmospheres from the surrounding protoplanetary disk. Yet here was a Jupiter-sized world, orbiting so close to its star that any water would be vaporized instantly. How could such a planet form? And how could it survive in such an extreme environment? The discovery of 51 Eridani b launched a revolution in planetary science. Within months, astronomers around the world were conducting their own radial velocity surveys, searching for the telltale stellar wobbles that would reveal hidden planets. The discoveries came thick and fast. 70 Virginis b, detected in 1996, was another hot Jupiter with a highly elliptical orbit that carried it from scorching proximity to its star to distances where water might briefly exist as liquid. 16 Cygni b, found the same year, had an orbit so eccentric that it resembled a comet more than a planet. Each new discovery challenged existing theories and revealed that planetary systems come in configurations never imagined by astronomers who had only our own solar system as a guide. Some planets orbited their stars backward. Others followed tilted orbits that were nearly perpendicular to their star's equator. Many gas giants had migrated inward from their formation sites, leaving behind chaotic debris fields where terrestrial planets might have tried to form. By the end of the 20th century, astronomers had detected over 24 exoplanets using the radial velocity technique. But these discoveries represented only the beginning. The most productive planet-hunting methods were yet to come. The transit method would prove to be the technique that truly opened the floodgates of exoplanet discovery. When a planet passes directly between its star and Earth, it blocks a tiny fraction of the star's light, causing the star to dim slightly for a few hours. This dimming is minuscule. For an Earth-sized planet crossing a molten, sun-like star, the brightness decreases by just 0.08%. Detecting such subtle changes requires extraordinary precision and patience. Astronomers must monitor thousands of stars continuously, watching for the periodic dimming that indicates a planet crossing the stellar disk. False alarms are common. Variable stars, eclipsing binary systems, and instrumental effects can all mimic planetary transits. The first successful transit detection came in 1999 when a team led by Greg Henry observed HD 209-458b, a hot Jupiter discovered earlier through radial velocity measurements. When the planet crossed its star's face, the star dimmed by exactly the amount predicted, confirming both the planet's existence and its size. This transit observation marked a breakthrough because it provided information that radial velocity measurements alone could not reveal. The depth of the transit told astronomers the planet's radius, while the duration revealed details about its orbital geometry. For the first time, scientists could determine a planet's density and begin to understand its internal structure. The power of the transit method became fully apparent with the launch of space-based observatories designed specifically for planet hunting. NASA's Kepler Space Telescope, launched in 2009, monitored over 150,000 stars simultaneously, looking for the subtle dimming signatures of transiting planets. Kepler's unprecedented precision and unblinking gaze transformed exoplanet science. The telescope could detect planets smaller than Earth, planets with ultra-short orbital periods measured in hours, and planets in multi-world systems where several bodies crossed their star's disk in complex choreographed sequences. The Kepler mission revealed that planets are extraordinarily common throughout the galaxy. Nearly every star appears to host at least one planet, and many stars harbor entire planetary systems. The telescope discovered thousands of confirmed planets and identified thousands more candidate worlds awaiting verification. Among Kepler's most remarkable discoveries was the TRAPPIST-1 system, announced in 2017. This red dwarf star, located 39 light-years from Earth, hosts 7 terrestrial planets, all similar in size to Earth. 3 of these worlds orbit within their star's habitable zone, where liquid water could potentially exist on their surfaces. The TRAPPIST-1 system resembles a scaled-down version of our solar system, with all 7 planets orbiting closer to their star than Mercury orbits our Sunday. Because red dwarfs are much cooler than the Sun, planets can maintain moderate temperatures despite these close orbital distances. Computer models suggest that the TRAPPIST-1 planets may be tidally locked, with one hemisphere permanently facing their star while the other remains in perpetual darkness. Such worlds would have extreme temperature contrasts between their day and night sides, but they might maintain liquid water in the twilight zone between light and shadow. The discovery of systems like TRAPPIST-1 demonstrates that habitable worlds may be far more common than anyone imagined. Red dwarfs comprise roughly 75% of all stars in the galaxy, and many appear to host terrestrial planets within their habitable zones. If even a small fraction of these worlds develop conditions suitable for life, the galaxy could harbor billions of inhabited planets. As ground-based surveys push the boundaries of what was possible from Earth's surface, space telescopes continue to expand the frontiers of exoplanet detection. The James Webb Space Telescope, launched in 2021, represents the current pinnacle of astronomical technology. JWST possesses capabilities that seemed like science fiction just decades ago. The telescope can analyze the atmospheric composition of exoplanets by studying how starlight filters through their atmospheres during transits. When a planet crosses its star's face, atoms and molecules in its atmosphere absorb specific wavelengths of starlight, creating a unique fingerprint that reveals the chemical composition of the planet's air. In 2022, JWST captured the first detailed atmospheric spectrum of an exoplanet, revealing water vapor, carbon dioxide, and clouds in the atmosphere of WASP 96b, a gas giant 800 light-years from Earth. This observation marked the beginning of a new era in exoplanet science, UHR, the era of atmospheric characterization. JWST's observations of exoplanet atmospheres provide insights that extend far beyond simple chemical inventory. The presence of water vapor indicates that a planet formed beyond the frost line and migrated inward. The abundance of carbon versus oxygen reveals details about the protoplanetary disk where the planet assembled. The structure of atmospheric clouds tells us about global circulation patterns and weather systems on alien worlds. For terrestrial planets orbiting nearby stars, JWST can search for biosignatures, EAI, atmospheric gases that might indicate the presence of life. Oxygen combined with water vapor would suggest photosynthesis. Phosphine or ammonia might indicate biological processes. Industrial pollutants could even reveal the presence of technological civilizations. The scope of exoplanet discovery continues to expand at a breathtaking pace. As of 2025, astronomers have confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. Ground-based surveys like the M-Earth project monitor nearby red dwarf stars, while space missions like TESS, the Transiting Exoplanet Survey satellite, scan the entire sky for planetary transits. Each new discovery adds another piece to the growing puzzle of planetary demographics. We now know that super-Earths, planets larger than Earth, but smaller than Neptune, are the most common type of world in the galaxy, even though our solar system contains none. We have found planets orbiting binary star systems, worlds with densities lower than Cork, and planets so close to their stars that they complete orbits in less than a day. The diversity of exoplanets has shattered our parochial assumptions about what planetary systems should look like. Far from being typical, our solar system appears to be somewhat unusual in its architecture. Most planetary systems discovered so far have massive planets orbiting very close to their stars, with orbital periods measured in days or weeks rather than years. This observational bias partly reflects the limitations of current detection methods, which are most sensitive to large planets orbiting close to their stars. But it also suggests that planetary migration is a common process that can dramatically reshape the architecture of planetary systems after their formation. As detection techniques continue to improve, astronomers are beginning to find more systems that resemble our own solar system, with gas giants orbiting at greater distances from their stars. These discoveries hint that solar system analogues may be more common than early surveys suggested. The treasure hunt for exoplanets has revealed that the galaxy is filled with worlds of almost unimaginable diversity. From hellish lava worlds orbiting white dwarf stars to frozen rogue planets drifting alone through interstellar space, the cosmos has proven far more creative in world-building than our most imaginative science fiction writers ever dared to dream. Yet perhaps the most profound discovery is not any individual exoplanet, but the recognition that planets are a cosmic commonplace. The night sky, which once seemed filled with lonely stars burning in isolation, is now known to teem with worlds. Nearly every point of light visible to the naked eye represents not just a star but an entire planetary system, a collection of worlds with their own unique histories, characteristics, and possibilities. This revelation has fundamentally changed humanity's cosmic perspective. We are not residents of a rare and special planetary system, but citizens of a galaxy where worlds are as common as grains of sand on a beach. The question is no longer whether other planets exist, but which of them might harbor life, and whether any of that life has achieved the complexity and intelligence necessary to contemplate the cosmos as we do. The greatest treasure hunt in history has succeeded beyond all expectations, revealing not just the existence of other worlds, but an entire universe filled with them. As we stand on the threshold of the next phase of exoplanet science, ISEA, the detailed characterization of potentially habitable worlds, we carry with us the humbling knowledge that Earth, for all its beauty and biological richness, is just one world among countless billions scattered throughout the cosmic dark. The art of finding planets around distant stars ranks among the most technically demanding endeavors in all of science. These worlds exist at the very limits of detectability, revealing themselves through changes so subtle that they approach the threshold of what is physically possible to measure. To understand the true magnitude of this achievement, We must appreciate the extraordinary precision required to hunt these invisible worlds across the vast darkness of interstellar space. Imagine trying to detect the motion of a person walking slowly while observing from a distance of 1,000 kilometers. This analogy captures the scale of precision needed for radial velocity measurements, ISA, the technique that revealed the first exoplanets. When a planet orbits a star, both objects actually orbit around their common center of mass, called the barycenter. For a system like Jupiter and the Sun, this barycenter lies just outside the Sun's surface, causing our star to wobble back and forth, with a maximum velocity of about 12 meters per second. But detecting this stellar wobble requires measuring velocities far smaller than anything in everyday experience. For Earth orbiting the Sun, the induced stellar wobble is just 9 centimeters per second, slower than a leisurely stroll. Modern spectrographs can detect stellar velocity changes as small as 1 meter per second, opening the possibility of finding planets as small as several Earth masses around nearby stars. The precision required is truly staggering. To achieve 1 meter per second accuracy, spectrographs must split starlight into thousands of individual wavelengths and measure the position of absorption lines to better than 1 part in 100 million. This is equivalent to measuring the thickness of a human hair to an accuracy of less than 1 nanometer. Atmospheric turbulence poses a constant challenge for ground-based observations. Earth's atmosphere causes stellar images to dance and shimmer, introducing random velocity errors that can easily overwhelm genuine planetary signals. Astronomers combat this problem by observing the same star hundreds of times over many years, using statistical techniques to separate real planetary wobbles from atmospheric noise. Temperature variations in the spectrograph instruments can also mimic planetary signals. A temperature change of just 1/1000th of a degree Celsius can shift spectral lines enough to fake the presence of a planet. Modern planet-hunting spectrographs are housed in temperature-controlled chambers and calibrated using hollow cathode lamps or laser frequency combs to achieve the stability needed for reliable measurements. The most sophisticated radial velocity instruments, such as HARPS, High Accuracy, Radial Velocity Planet Searcher, in Chile, and HIRA's High Resolution Echelle Spectrometer, in Hawaii, represent marvels of precision engineering. These instruments can track the velocity of a star over decades with accuracy, sufficient to detect Earth-mass planets in the habitable zones of nearby Sun-like stars. The transit method presents different but equally formidable technical challenges. When a planet passes in front of its star as seen from Earth, it blocks a tiny fraction of stellar light. For an Earth-sized planet crossing a Sun-like star, this dimming amounts to just 84 parts per million, a brightness decrease of 0.08 of 1%. Detecting such minute changes requires photometric precision that pushes the boundaries of current technology. Ground-based telescopes must contend with atmospheric scintillation, the twinkling effect that makes stars appear to vary in brightness. Clouds, atmospheric water vapor, and even high-altitude aircraft can introduce spurious signals that mimic planetary transits. Space-based observatories avoid atmospheric interference, but face their own technical hurdles. The Kepler Space Telescope achieved unprecedented photometric precision by using an array of 42 charge-coupled device (CCD) detectors, each containing over 2 million pixels. The telescope monitored the same field of stars continuously for over 4 years, accumulating billions of individual brightness measurements. Kepler's precision was so extraordinary that it could detect brightness variations smaller than 10 parts per million, equivalent to noticing when a single light bulb is turned off in a city of 100,000 lights. This precision enabled the discovery of planets smaller than Earth, including worlds barely larger than Mars. But detecting a planetary transit is only the beginning. Confirming that the signal represents a genuine planet requires eliminating numerous false positive scenarios. Eclipsing binary stars can mimic planetary transits, as can background stars that happen to align with the target star. Even systematic instrumental effects can create periodic dimming that resembles a planetary signature. Astronomers have developed sophisticated techniques to distinguish genuine planets from imposters. Follow-up observations using different telescopes and instruments help confirm planetary signals. Radial velocity measurements can verify that the transiting object has the appropriate mass for a planet rather than a brown dwarf or small star. The most challenging false positives involve hierarchical triple star systems, AET, configurations where a distant star gravitationally bound to the target star happens to host its own eclipsing binary companion. The combined light from all three stars can create a signal that perfectly mimics a large planet transiting the nearest star. Only detailed spectroscopic analysis can reveal the true nature of such systems. Statistical validation techniques have become increasingly important as transit surveys discover thousands of planetary candidates. Rather than requiring definitive confirmation of each individual planet, astronomers use probabilistic arguments to validate populations of similar candidates simultaneously. This approach has enabled the validation of thousands of Kepler planets that would be too faint for traditional follow-up observations. Direct imaging of exoplanets represents the ultimate technical challenge in planet detection. Unlike radial velocity and transit methods, which detect planets indirectly through their gravitational or geometric effects on their host stars, direct imaging attempts to photograph the planets themselves. The fundamental problem is contrast. Planets are billions of times fainter than their host stars. Detecting a planet next to its star is like trying to see a firefly hovering beside a powerful searchlight from thousands of kilometers away. For planets in the habitable zones of nearby stars, the contrast ratio can exceed 10 billion to 1 in visible light. Adaptive optics systems help ground-based telescopes overcome atmospheric turbulence by using deformable mirrors that adjust hundreds of times per second to correct for atmospheric distortions. These systems can achieve image quality limited only by the fundamental properties of the telescope rather than atmospheric seeing. Coronagraphs block the overwhelming glare of host stars, revealing the faint light of orbiting planets. The most advanced coronagraphs use sophisticated optical techniques such as vortex phase masks, star shades, or nulling interferometry to suppress starlight by factors of millions or billions while preserving the light from nearby planets. The first direct image of an exoplanet came in 2004 when astronomers using the Very Large Telescope in Chile photographed 2M1207b, a planetary mass object orbiting a brown dwarf 170 light-years from Earth. This achievement required years of technological development and represented a triumph of precision optics and image processing. Subsequent direct imaging surveys have discovered dozens of young massive planets orbiting relatively far from their host stars. These systems are detectable because young planets retain heat from their formation and glow with thermal radiation in infrared wavelengths. The large orbital separations help reduce the contrast between planet and star, making detection feasible with current technology. Future direct imaging missions will target older, cooler planets that shine primarily by reflected starlight. NASA's proposed HABEX, Habitable Exoplanet Observatory, and LUVOR Large, Ultraviolet Optical Infrared Surveyor missions could directly image Earth-like planets around nearby Sun-like stars and analyze their atmospheric composition for signs of life. Gravitational microlensing exploits Einstein's prediction that massive objects warp space-time and focus light like a lens. When a planet passes precisely between Earth and a background star, the planet's gravity can temporarily brighten the background star by focusing its light toward Earth. These microlensing events are extraordinarily rare and unpredictable. The alignment must be nearly perfect. Any deviation by more than the apparent size of the lensing star as seen from Earth will prevent the effect from occurring. For typical stellar masses and distances, useful microlensing events happen roughly once per million stars per year. Despite their rarity, Microlensing events provide unique capabilities for planet detection. The technique is sensitive to planets at any distance from Earth and can detect worlds that would be impossible to find using other methods. Microlensing has discovered planets orbiting stars near the galactic center, 25,000 light-years away, and may have detected the first examples of rogue planets, worlds ejected from their birth systems to wander alone through interstellar space. The duration and detailed shape of microlensing events reveal the masses and orbital separations of both the lensing star and any planets it hosts. Because each microlensing event is unique and cannot be repeated, confirming planetary detections requires careful analysis of the light curve. The precise pattern of brightness changes as the lensing system moves across the background star. Astrometry, the precise measurement of stellar positions, offers another approach to planet detection. As planets orbit their host stars, they cause the stars to move in small ellipses against the background sky. For nearby stars, these positional changes might be large enough to detect with sufficiently precise measurements. The European Space Agency's Gaia mission, launched in 2013, is conducting the most precise astrometric survey in history. Gaia measures stellar positions with accuracy better than 10 microarcseconds, equivalent to detecting the apparent width of a human hair seen from a distance of 1,000 kilometers. Over its multi-year mission, Gaia will detect thousands of exoplanets through their astrometric signatures. The technique is particularly sensitive to massive planets in wide orbits around nearby stars, exactly the types of worlds that are most difficult to detect using radial velocity or transit methods. Future astrometric missions could achieve even greater precision, potentially detecting Earth-mass planets around nearby stars through their gravitational perturbations. Such measurements would provide direct determinations of planetary masses and three-dimensional orbital geometries, complementing information from other detection techniques. The combination of multiple detection methods provides the most complete picture of exoplanetary systems. Radial velocity measurements reveal planetary masses and orbital eccentricities. Transit observations determine planetary radii and atmospheric properties. Direct imaging provides information about atmospheric composition and thermal structure. Microlensing and astrometry access different regions of parameter space, detecting planets that other methods might miss. This multi-technique approach has revealed the extraordinary diversity of exoplanetary systems. Some planets orbit their stars in highly eccentric ellipses that carry them from scorching proximity to frozen isolation. Others follow circular orbits tilted at extreme angles relative to their stellar equators. Many giant planets have migrated inward from their formation sites, while others may have been scattered outward by gravitational interactions. The precision required for exoplanet detection continues to push technological boundaries. Next-generation instruments promise even greater capabilities: radial velocity, precision, approaching 10 centimeters per second, photometric accuracy of parts per billion, and direct imaging, contrasts exceeding 10 billion to 1. These advances will enable the detection and characterization of truly Earth-like planets around nearby Sun-like stars. For the first time in human history, we may soon possess the technological capability to search for signs of life on other worlds by analyzing the atmospheric composition of potentially habitable exoplanets. The quest to hunt invisible worlds has driven innovations that benefit far beyond astronomy. Precision spectroscopy techniques developed for exoplanet detection find applications in laser physics and atomic clocks. Advanced adaptive optic systems improve medical imaging and industrial inspection. Statistical methods for validating planetary candidates enhance data analysis across numerous scientific disciplines. Perhaps most remarkably, the techniques for hunting invisible worlds have revealed that such worlds are not invisible at all. They are everywhere, waiting patiently for sufficiently sensitive instruments to reveal their presence. The cosmos has proven to be far more richly populated with planets than anyone dared imagine, transforming our understanding of our place in the universe and setting the stage for the next great adventure in human exploration. Indy 8. The search for life among the stars. Every answer in planetary science seems to birth new questions, each discovery opening doors to chambers filled with even deeper mysteries. As our census of exoplanets has grown from a handful to thousands, patterns have emerged that challenge our most fundamental assumptions about how planetary systems form and evolve. These cosmic puzzles keep astronomers awake at night, not because they represent failures of understanding, but because they hint at processes and phenomena we have barely begun to comprehend. The mystery that perhaps troubles planetary scientists most deeply concerns the hot Jupiters, a massive gas giant planets that orbit closer to their stars than Mercury orbits our Sunday. According to every model of planetary formation, these worlds should not exist. Gas giants like Jupiter form beyond the frost line in protoplanetary disks, where temperatures are cold enough for water to freeze into ice. This frozen water provides the solid material needed to build massive planetary cores, typically 10 to 15 times Earth's mass, large enough to gravitationally capture thick hydrogen and helium atmospheres from the surrounding disk. Inside the frost line, where temperatures exceed several hundred degrees Celsius, water exists only as vapor. Without abundant solid materials, planetary cores remain small, never achieving the mass needed to become gas giants. The inner regions of protoplanetary disks should produce only terrestrial planets, rocky worlds like Earth, Venus, and Mars. Yet hot Jupiters are among the most common types of exoplanets discovered around Sun-like stars. These worlds have masses comparable to Jupiter, but complete their orbits in just a few days, racing around their host stars at distances where surface temperatures exceed 1,000 degrees Celsius. Some hot Jupiters orbit so close to their stars that their atmospheres are being stripped away by intense stellar radiation, creating comet-like tails of escaping gas. The obvious explanation is planetary migration. Hot Jupiters must form beyond the frost line and then spiral inward toward their host stars. But this migration process poses its own puzzles. Computer simulations suggest that migrating gas giants should continue spiraling inward until they plunge into their stars and are destroyed. What mechanism allows hot Jupiters to halt their inward migration at stable close-in orbits? Several theories attempt to explain hot Jupiter migration. Gravitational interactions with the protoplanetary disk could cause inward migration, with the planet eventually stopping when the disk dissipates. Alternatively, gravitational interactions with other planets in the system might scatter a gas giant onto a highly eccentric orbit that brings it very close to its star. Tidal forces would then circularize this orbit, creating a hot Jupiter. But each migration mechanism makes specific predictions about the orbital and atmospheric properties of hot Jupiters, and observations have revealed a bewildering diversity that no single theory can explain. Some hot Jupiters orbit their stars in the same direction as stellar rotation, while others orbit backward. Some have circular orbits perfectly aligned with their star's equator, while others follow tilted or highly eccentric paths. The atmospheric compositions of hot Jupiters add another layer of mystery. These worlds should have lost their primordial hydrogen and helium atmospheres to stellar winds and ultraviolet radiation. Yet many hot Jupiters retain thick atmospheres that appear surprisingly similar to Jupiter's composition. How do these worlds maintain their gaseous envelopes in such extreme environments? Even more puzzling is the discovery that hot Jupiters appear to be relatively rare around stars more massive than the Sunday. If hot Jupiters form through disk migration, this mass dependence suggests that the properties of protoplanetary disks vary systematically, with stellar mass in ways we do not yet understand. The mystery of super-Earths presents a different but equally profound puzzle. These worlds, planets with masses between Earth and Neptune, are the most common type of planet discovered around other stars. Statistical analyses of Kepler data suggest that virtually every Sun-like star hosts at least one super-Earth, making them the galactic norm for planetary systems. Yet our solar system contains no super-Earths whatsoever. The mass gap between Earth and Neptune in our solar system spans a factor of 17, a chasm that contains the most common planetary type in the galaxy. This absence is so striking that astronomers sometimes refer to our solar system as the super-Earth desert. Why did our solar system fail to produce any super-Earths when they appear to be cosmic commonplace? Elsewhere, several theories attempt to explain this absence, but none are entirely satisfactory. One possibility is that super-Earths did form in our solar system but were subsequently destroyed or ejected. Jupiter's early inward migration might have cleared out the inner solar system, preventing super-Earth formation or scattering existing super-Earths into the Sun or out of the system entirely. Alternatively, the particular conditions in our protoplanetary disk, perhaps its mass, composition, or evolution timescale, might have favored the formation of terrestrial planets rather than super-Earths. But this explanation implies that our solar system formed under unusually specific conditions, making it an outlier among planetary systems. The internal structure and composition of super-Earths remain largely mysterious. These worlds might be scaled-up versions of terrestrial planets, with rocky mantles and iron cores, but they could also be mini-Neptunes with substantial hydrogen and helium atmospheres surrounding smaller rocky cores. Or they might be water worlds with global oceans hundreds of kilometers deep overlying rocky interiors. The diversity of possible super-Earth compositions has profound implications for habitability. Rocky super-Earths with thin atmospheres might provide stable climates suitable for liquid water and life. But super-Earths with thick hydrogen atmospheres would experience extreme greenhouse effects that could sterilize their surfaces. Distinguishing between these possibilities requires precise measurements of super-Earth masses and radii, combined with atmospheric observations that can reveal their compositional properties. Such measurements are technically challenging but essential for understanding whether super-Earths represent potential havens for life or inhospitable worlds shrouded in crushing atmospheres. Perhaps the most haunting planetary mystery concerns the rogue planets, HS, worlds that wander through interstellar space without any host star, ejected from their birth systems to drift alone through the cosmic void. Gravitational interactions during the chaotic early evolution of planetary systems can accelerate planets to velocities exceeding their system's escape speed. Once ejected, these rogue worlds become orphans of the galaxy, condemned to billions of years of solitary wandering through the darkness between stars. The first confirmed rogue planet, PSOJ 318, 5-22, was discovered in 2013 using infrared telescopes in Hawaii. This world has a mass about 6 times Jupiter's, but orbits no star. Its surface temperature of approximately 800 degrees Celsius comes entirely from internal heat, 18.2. The residual warmth from its formation, plus energy released by the radioactive decay of elements in its interior. Computer simulations suggest that rogue planets might be incredibly common. Some models predict that the Milky Way contains billions of these wandering worlds, if perhaps even more rogue planets than stars. If this prediction is correct, rogue planets would represent a vast hidden population of worlds that vastly outnumbers the planetary systems we can directly observe. The existence of rogue planets raises profound questions about habitability in seemingly impossible environments. Without stellar heating, rogue planet surfaces would be frozen solid, with temperatures approaching absolute zero. But internal heat sources might maintain liquid water beneath thick ice shells, similar to conditions in the subsurface oceans of Jupiter's moon Europa. Some rogue planets might retain thick hydrogen atmospheres that provide greenhouse warming, maintaining surface temperatures above the freezing point of water despite their isolation from stellar heat. Such worlds could potentially harbor life in environments completely disconnected from stellar energy sources. The detection of rogue planets poses extraordinary technical challenges. These worlds emit no reflected light, and reveal themselves only through their own thermal radiation or gravitational effects. Most rogue planet discoveries rely on gravitational microlensing, do, temporary brightening of background stars when rogue planets pass precisely between Earth and distant stellar targets. Future infrared space telescopes might be capable of conducting systematic surveys for rogue planets by detecting their thermal emission directly. Such surveys could reveal whether these wandering worlds are truly as common as theoretical models predict. The orbital architecture of multi-planet systems provides another source of persistent mystery. Many exoplanetary systems exhibit configurations that seem to defy gravitational stability. Planets follow highly eccentric orbits that should lead to close encounters and eventual collisions. Others maintain resonant chains, where orbital periods are related by simple ratios, despite the chaotic processes that likely characterize their formation. Perhaps most puzzling are the systems where planets orbit at angles that are completely misaligned with their host star's rotation. Some planets follow polar orbits that carry them over their star's poles, while others orbit retrograde, backward compared to their star's spin. These misaligned orbits suggest violent dynamical histories involving planetary collisions, close encounters with passing stars, or other catastrophic events. HD 80b exemplifies these mysteries. This planet orbits its star backward and at an angle of approximately 130 degrees relative to the stellar equator. Computer simulations suggest that such extreme misalignment might result from gravitational interactions with a distant companion star that gradually tilted the planet's orbit over millions of years. The prevalence of misaligned systems has forced astronomers to abandon the assumption that planetary systems form and evolve in orderly, predictable ways. Instead, chaos and violence appear to be common themes in planetary system evolution, with many worlds experiencing dramatic orbital changes long after their initial formation. The mystery of planetary system architecture extends to questions about the frequency of solar system analogues. Most detected exoplanetary systems differ dramatically from our solar system in their orbital configurations, planet types, and overall architecture. This raises the unsettling possibility that our solar system might be highly unusual, perhaps even unique, in its particular combination of characteristics. Recent surveys have begun detecting more distant giant planets, with orbital periods measured in years rather than days or weeks. These discoveries suggest that solar system analogues might be more common than early planet hunting surveys indicated. But current detection techniques remain biased toward close-in planets, making it difficult to assess the true frequency of systems resembling our own. The atmospheric dynamics of exoplanets present yet another frontier of mystery. Observations have revealed worlds with atmospheric circulation patterns that defy simple expectations. Some hot Jupiters have dayside temperatures that exceed nightside temperatures by thousands of degrees, while others show surprisingly uniform temperature distributions around their entire circumference. Cloud formation and atmospheric chemistry on exoplanets operate under conditions that have no analogues in our solar system. Worlds with temperatures exceeding 1000 degrees Celsius might have clouds made of molten silicate rock or metallic vapor. Others might experience precipitation of liquid metals or exotic compounds that exist nowhere on Earth. The search for atmospheric biosignatures, FAO, gases that might indicate the presence of life, FAO, faces the challenge of distinguishing biological signals from non-biological processes that can produce similar atmospheric compositions. Oxygen, often cited as a potential biosignature, can be produced by photolysis of water vapor in planetary atmospheres. Methane can be generated by geological processes as well as biological ones. Perhaps the deepest mystery of all concerns the fundamental question that drives much exoplanet research. How common is life throughout the galaxy? The discovery of thousands of exoplanets has shown that worlds are abundant, but abundance alone does not guarantee habitability, and habitability does not ensure the emergence of life. The transition from non-living chemistry to living systems remains one of the most profound unsolved problems in science. We know that this transition occurred at least once, on Earth roughly 4 billion years ago, but we have no direct evidence that it has happened anywhere else. As our technological capabilities approach the threshold, where we might detect signs of life on other worlds, these mysteries take on urgent practical importance. The atmospheric composition of potentially habitable exoplanets will provide our first opportunity to search for extraterrestrial life, but interpreting these observations will require a much deeper understanding of planetary formation, evolution, and atmospheric chemistry than we currently possess. The mysteries that haunt the night sky remind us that the universe is far stranger and more complex than our theories anticipated. Each answered question reveals new depths of ignorance, new frontiers of discovery waiting to be explored. In this sense, the greatest achievements of exoplanet science may not be the worlds we have discovered, but the mysteries we have uncovered, puzzles that will challenge and inspire future generations of astronomers as they continue humanity's quest to understand our place among the stars. We stand today at one of the most extraordinary moments in the history of human discovery. After millennia of wondering whether life exists beyond Earth, we are finally developing the technological capabilities to begin answering this ultimate question. The next 2 decades will witness the opening of new windows to distant worlds, windows that may reveal whether we are alone in the universe or part of a vast, the community of life scattered among the stars. The James Webb Space Telescope, humanity's most ambitious observatory, has already begun transforming our understanding of exoplanets in ways that seemed impossible just years ago. Positioned at the second Lagrange point, 1.5 million kilometers from Earth, JWST operates in the frigid environment of deep space where its instruments can achieve unprecedented sensitivity to infrared radiation. When an exoplanet transits across the face of its host star, some starlight filters through the planet's atmosphere before reaching Earth. Atoms and molecules in that atmosphere absorb specific wavelengths of light, creating a unique spectroscopic fingerprint that reveals the chemical composition of alien air. JWST's extraordinary sensitivity allows it to read these fingerprints for planets orbiting stars hundreds of light-years away. The telescope's first exoplanet atmospheric analysis, released in 2022, examined WASP-96b, a gas giant 800 light-years from Earth. The resulting spectrum revealed water vapor, carbon dioxide, and even clouds in the planet's atmosphere. For the first time in human history, we had tasted the air of another world. But JWST's true revolutionary potential lies in its ability to analyze the atmospheres of rocky planets orbiting in the habitable zones of nearby red dwarf stars. Red dwarfs comprise roughly 75% of all stars in the galaxy, and many host terrestrial planets at distances where liquid water could exist on their surfaces. The TRAPPIST-1 system represents JWST's most tantalizing target. This nearby red dwarf hosts 7 Earth-sized planets, 3 of which orbit within the habitable zone. JWST can analyze the atmospheric composition of these worlds, searching for the chemical signatures that might indicate the presence of life. Water vapor in a planet's atmosphere suggests that liquid water might exist on the surface. Oxygen, combined with water vapor, could indicate photosynthesis. 4. The process by which plants and bacteria convert sunlight into chemical energy while releasing oxygen as a waste product. The simultaneous presence of oxygen and methane would be even more compelling, since these gases react with each other and disappear from atmospheres unless continuously replenished by biological processes. JWST might even detect more exotic biosignatures. Phosphine, a gas produced by certain microorganisms, has been proposed as a potential sign of life. Dimethyl sulfide, produced by marine algae on Earth, could indicate biological activity in the oceans of water worlds. Industrial pollutants, such as chlorofluorocarbons, might reveal the presence of technological civilizations. The detection of any confirmed biosignature would represent the most profound discovery in human history. It would prove that life is not unique to Earth, but can emerge and flourish on other worlds throughout the galaxy. Such a discovery would forever change humanity's understanding of our place in the cosmic order. But atmospheric analysis represents only the beginning of our expanding capabilities to study exoplanets. The next generation of ground-based telescopes will push the boundaries of what is possible from Earth's surface. The Extremely Large Telescope, ELT, currently under construction in Chile's Atacama Desert, will dwarf all existing observatories. Its primary mirror, 39 meters in diameter, will collect 16 times more light than any current telescope. This light-gathering power, combined with revolutionary adaptive optics systems, will enable the ELT to directly photograph Earth-like planets orbiting nearby Sun-like stars. Direct imaging of exoplanets represents the ultimate goal of planet-hunting astronomy. Unlike transit spectroscopy, which can only study planets that happen to cross their star's face as seen from Earth, direct imaging can analyze any planet orbiting within a pound's certain distance of its host star. This technique will reveal planets in face-on orbital planes that would never produce transits. The ELT's adaptive optics system will use thousands of deformable mirror segments to correct for atmospheric turbulence in real time. Sophisticated coronagraphs will block the overwhelming glare of host stars, revealing the faint reflected light of orbiting planets. These technological marvels will achieve contrast ratios exceeding 10 billion to 1, equivalent to detecting a firefly next to a searchlight from thousands of kilometers away. For the first time, astronomers will be able to study the seasonal variations of potentially habitable worlds. As these planets orbit their stars, different hemispheres will be illuminated, revealing weather patterns, cloud formations, and possibly even the changing colors associated with vegetation cycles. The search for life will extend beyond individual planetary observations to encompass entire stellar neighborhoods. NASA's proposed Roman Space Telescope will conduct a comprehensive census of exoplanets around nearby stars using gravitational microlensing. This technique can detect planets at any orbital distance, including Earth-like worlds in the habitable zones of Sun-like stars. Future space missions will take exoplanet science even further. The proposed Habitable Exoplanet Observatory, HABEX, would use a starshade, a precisely positioned external occulter, to block starlight and enable direct imaging of potentially habitable worlds. The starshade, flying in formation with the telescope at distances of tens of thousands of kilometers, would cast a shadow that allows the telescope to photograph planets directly. Even more ambitious is the proposed Large Ultraviolet Optical Infrared Surveyor, LUVOIR, a space telescope with a mirror up to 15 meters in diameter. LUVOIR would have the capability to directly image and analyze the atmospheres of hundreds of potentially habitable exoplanets, conducting a comprehensive survey of life in our cosmic neighborhood. The most audacious proposals involve sending robotic probes to nearby exoplanets themselves. The Breakthrough Starshot initiative aims to develop technology capable of accelerating tiny spacecraft to 20% the speed of light using powerful ground-based lasers. These postage stamp-sized probes would reach Proxima Centauri b, MD, the nearest potentially habitable exoplanet, in approximately 20 years. Upon arrival, these interstellar messengers would transmit the first close-up images of an alien world. They might reveal continents and oceans, ice caps and weather systems, perhaps even signs of life visible from space. Such observations would provide ground truth for our remote sensing techniques and revolutionize our understanding of planetary evolution. The technical challenges of interstellar travel remain formidable. Accelerating even tiny spacecraft to relativistic speeds requires enormous energies and precision engineering beyond current capabilities. The spacecraft must survive the journey through interstellar space, where collisions with microscopic dust grains could be catastrophic at such high velocities. Communication across interstellar distances poses additional difficulties. Radio signals from Proxima Centauri would take over 4 years to reach Earth, making real-time control impossible. The spacecraft must operate autonomously, making critical decisions about observations and data transmission without human intervention. Yet the potential scientific return justifies these extraordinary technical demands. Direct observations of an exoplanet would provide unprecedented insights into planetary formation, atmospheric evolution, and the potential for life on worlds very different from those in our solar system. As our observational capabilities expand, the search for life will become increasingly sophisticated. Rather than looking for individual biosignatures, astronomers will analyze entire atmospheric profiles to distinguish living worlds from sterile ones. Living planets should exhibit chemical disequilibrium, AMA, combinations of gases that would not coexist without continuous biological processes to maintain them. Earth's atmosphere provides the template for such analyses. Our planet's atmosphere contains 21% oxygen and trace amounts of methane, gases that react with each other and would disappear within thousands of years without biological processes to replenish them. The simultaneous presence of these reactive gases creates a chemical signature that could be detectable on exoplanets using next-generation telescopes. But life elsewhere might use biochemistry very different from Earth's biology. Planets with different atmospheric compositions, surface pressures, or energy sources might host life forms that produce entirely different sets of atmospheric gases. Identifying such exotic biosignatures will require a deep understanding of alternative biochemistries and planetary environments. The search for technological signatures represents another frontier in exoplanet science. Industrial civilizations might leave detectable fingerprints in their planetary atmospheres through pollution, energy production, or terraforming activities. Artificial lights on the night sides of planets could be detectable with sufficiently sensitive telescopes. Even more speculatively, advanced civilizations might construct megastructures that partially block their host star's light, creating periodic dimming patterns that could be distinguished from natural phenomena. The star KIC 8462852, informally known as Tabby's star, exhibited mysterious dimming events that briefly inspired speculation about alien megastructures. Though subsequent observations favor natural explanations involving circumstellar dust, the implications of detecting life, IA, whether microbial, complex, or technological, extend far beyond astronomy. Such discoveries would profoundly impact philosophy, religion, sociology, and virtually every aspect of human culture. The knowledge that life exists elsewhere would force humanity to reconsider our significance in the cosmic order and our responsibilities as a potentially spacefaring species. If microbial life proves common throughout the galaxy, it would suggest that the transition from non-living chemistry to biological systems is relatively straightforward under appropriate conditions. This would bode well for the prevalence of life, but would still leave open questions about the likelihood of complex, multicellular organisms. The discovery of complex life, MS, organisms comparable to Earth's plants and animals, would be even more significant. It would suggest that evolution can produce sophisticated biological systems on multiple worlds, making it more likely that intelligence and technology might also emerge elsewhere. Perhaps most profound would be the detection of technological civilizations through their atmospheric signatures or artificial constructions. Such a discovery would prove that intelligence can evolve from biological origins and develop technologies capable of planetary-scale engineering. It would also raise immediate questions about communication and the possibility of contact. As we stand on the threshold of these discoveries, it is worth reflecting on the journey that has brought us to this point. From ancient observers tracking wandering stars, to modern astronomers analyzing the atmospheres of worlds hundreds of light-years away, humanity has pursued knowledge of other worlds with persistent curiosity and ingenuity. The next 2 decades will likely answer questions that have haunted human imagination for millennia. Are we alone in the universe? Is life common or rare among the stars? Do other planets host biospheres as rich and complex as Earth's? Might we discover worlds where intelligence has emerged and technology has flourished? These questions may soon transform from eternal mysteries into answered facts. The windows opening to new worlds promise to reveal not just the existence of other planets, but the possibility of other life, other intelligence, other civilizations sharing our galaxy. Consider the magnitude of this moment. You are living during the first generation in human history with the technological capability to search for life on other worlds. Your contemporaries may be the first humans to learn whether Earth's biosphere is unique or part of a vast community of living worlds scattered throughout the cosmos. The search for life among the stars represents humanity's greatest adventure, a quest that combines our most sophisticated technologies with our deepest philosophical questions about the nature of life, intelligence, and our place in the universe. As new windows open to distant worlds, we approach answers that will forever change our understanding of what it means to be human in a universe that may be teeming with life. The story of planets, 24, from the wandering stars that puzzled ancient astronomers to the potentially habitable worlds now within reach of our instruments, continues to unfold. Each new discovery adds another chapter to this cosmic narrative, revealing a universe far stranger, more diverse, and more wonderful than our ancestors ever dared imagine. The greatest discoveries may still lie ahead, waiting in the light of distant stars, in the atmospheres of alien worlds, in the possibility that somewhere among the billions of planets in our galaxy, other eyes are looking back at us across the cosmic dark, wondering if they too are alone among the stars.